Here is how I prepare for a physics Olympiad, specifically mechanics. After extremely extensive research, I'm going to go through point by point of the syllabus of the International Physics Olympiad. Please note that this is not an exhaustive list and use that as a starting point only. I'm also going to be assuming that you're familiar with the more basic non-calculus based physics typically taught in school. The first thing to look at is the displacement vector. So in physics Olympiads, often you'll be dealing with 2 or 3 dimensions. The displacement vector, in this case we've just called it R, can have components X, Y, and Z in each of the 3 dimensions. These can often depend on time as well. For instance, if I had a particle here, this could have its displacement from the origin being a certain value up the Z coordinate, in this case it lies on the Y coordinate, and a certain displacement from the X coordinate. The velocity of that particle will be given by the derivative of the displacement vector, and the X component can be differentiated separately, the Y component and the Z component as well. The inverse is also true, so if we wanted to find the displacement, we could integrate the velocity with respect to time. This is typically a definite integral, so I'm just going to say from t1 to t2. However, it can also be an indefinite one, and then use the boundary conditions to determine the constants of integration. Please note that in this case, the linear velocity, if something is moving in a curve or in a circle, will lie on the tangent. We can also define our acceleration to be the derivative of the velocity, and this of course will make that the second derivative of the displacement vector. Additionally, you can also think of the velocity as the integral of the acceleration with respect to time, once again between 2 set times, and we can look at the acceleration in each of the individual directions. If something is moving in a circle in particular, it's often convenient to look at the normal acceleration and essentially the centripetal acceleration towards the center, and also the tangential acceleration. But more on that later. If we have uniform motion, then we can express each of the coordinates as x is equal to vxt plus some initial displacement. So that change of displacement in the x direction will be given by vx t, which is essentially the distance traveled in that direction. Similarly, in the y direction, this will be vyt, where speed times time essentially just gives us the distance in that particular direction. And overall, the displacement vector can be written as the velocity multiplied by the time elapsed plus that initial coordinate r0. Well, if we look closely, this is essentially just the equation of a straight line. Y is equal to mx plus c, typical in the UK. If you're studying somewhere else, different countries use different symbols for this. That's a whole different story. But if you had a graph of the displacement against time, then velocity will be given, will be the gradient, and r0, the initial displacement, will be the y-intercept. Here's an example of the velocity in the z direction, starting from just about 0, and it will be a nice straight line. Moving on, we have the displacement r against t, and if we have a positive gradient, that's going to correspond to a positive velocity. If we have a negative gradient, such as this one, that's going to correspond to negative velocity. In the case of uniform motion, a v against t graph is just a nice little straight line for the origin, and the displacement in that case will just be given by the area. Nice and simple. We don't need to integrate to figure out the area. We can just multiply a few of those together. Please don't forget that particularly in the regional rounds of the competitions, you'll probably be using the uniform acceleration equations, the SUVAT equations as we call them in the UK, to work out problems in projectile motion, for instance. So we have v is equal to u plus at, where v is the final speed, u is the initial speed. Notice that if we were to integrate this expression with respect to time, we're going to get the displacement. If we integrate u, we're going to get ut plus, now the integral of t squared if the acceleration is constant is just a half a t squared. So now we see where this equation is actually coming from. This particular equation as well is very, very useful for determining things such as maximum height. I'm not going to go into too much detail on these because I already have some very specific videos, and if you'd like some extra practice with these, I'll link them in the description below. And now let's have a look at some Olympiad level practice using these new concepts. These problems typically appear in regional Olympiads. I'm going to be demonstrating this with a problem from the British Physics Olympiad from 2018 round 1. So we have the displacement of an object is given by this function. We can see that it depends on time. So what we need to do is figure out the time when the object comes to a rest. Okay, well, in order to do so, we're going to need to find the time derivative, because if the object is at rest, this means that the actual speed will be equal to 0. In other words, we can say that ds by dt, which is equal to the speed, is 0. Well, let's differentiate this function. So what is that going to give us? That's going to give me 6t squared, take away 18t plus 12, and then the 4 is a constant, so we can just get rid of that. That's equal to 0. And this here is actually going to be our expression for the speed or the time derivative. What I'm going to do is I'm going to divide all of these sides, both of these sides by 6, and then I'm going to get t squared take away 3t plus 2 is equal to 0. Luckily for us, this is totally factorizable. So what is that going to give me? T minus 1, and then t take away 2 is equal to 0, giving me 2 times when the speed is 0, and that is at t is equal to 1 second, or at t is equal to 2 seconds. Okay. And the next one, the time when the acceleration is 0. So this here was part I. The second part, II, we're going to be looking for the acceleration. Now, the acceleration, as we said, is equal to the second time derivative of the displacement, which is also equal to the first time derivative of the velocity. In other words, we need to differentiate this expression yet again with respect to time. Okay, well, this here is going to give me 12t take away 18, and this is essentially my acceleration. The question though is asking us the time when the acceleration is equal to 0. So I'm going to say that 12t take away 18 is equal to 0. Now we can simplify this a little bit. What that give me is 2t take away 3 just by dividing by 6 is equal to 0. And this means that the time will just be equal to 3 over 2, which is 1.5 seconds. Okay, part 3, the object's velocity when the acceleration is 0. Okay, this doesn't seem so bad because we already have an expression for the velocity here. So all we need to do is just plug this value into this expression. 6 times 1.5 squared take away 18 times 1.5 plus 12, and this should just give me the answer. And after some calculator magic, we're going to find that this is equal to minus 1.5 meters per second. Okay, we've done part 3. Part 4, the object's acceleration when its velocity is 0. Okay, so this occurs at 2 times t is equal to 1 second or t is equal to 2 seconds, and we have a couple of expressions. We're going to have a couple of expressions for the acceleration. So when t is equal to 1 second, wasn't it? Yeah, 1 and 2, and when
t is equal to 2 seconds. We are going to find that the expression for the acceleration was 12t take away 18, so the acceleration at t is equal to 1 second will just be 12 times 1, which is just 12, take away 18, will that give me minus 6 meters per second squared. Now when t is equal to 2 seconds, well, this here will be 12 times 2, take away 18, which is, what is that, 24, take away 18, that's plus 6. So you can see that it varies quite a lot in 1 second. I also made up a little problem to illustrate the inverse of this. So the acceleration of an object which starts from rest is given by the following expression. Find the velocity of the object 10 seconds after the start. Okay, so velocity is just simply the integral of the acceleration, which is now a function of time with respect to time. So what I'm going to need to do is essentially just integrate this entire expression, because g, that's just a constant. I'm going to take that outside of the integral sign, and what I'm going to be left with is the integral of t over 5 take away t squared over 25 with respect to time. So this here will just give me g, and this is actually a definite integral between 0 and 10 seconds. Integrating this, we're going to get t squared over 2 times 5 is just 10, take away t to the power of 3 over 25 times 3, which is just 75, and this integral here is going to be evaluated between 0 and 10, and this here will give me around minus 32.7 meters per second at t is equal to 10 seconds.
Now let's move to circular motion. First we'll consider just uniform circular motion with the no slip condition. Here is a circle, and the basic equation, the definition of the angle, is that s is equal to r theta, where s is just an arc length along this circle from here to here. The angle is theta and the radius is r. We can define the angular velocity as d theta by dt, the first time derivative. Now, typically we say that this is measured in radians per second, but please know that the radian is not a real unit. Why is that? Because if we think about it, theta is going to equal to s over r. S is measured in meters, r is measured in meters, so theta is actually a unitless quantity. However, we tend to call it just radians per second to give us a good idea of a measure. However, the SI unit is still s to the power of -1. So since theta is equal to s over r, we can take the time derivative of it, and we can say that omega is the theta by dt. So this means that this will be ds over r, all of this differentiated. However, because the radius is a constant, we're assuming a perfect circular motion, then we can take that outside of the derivative. So what we're left with is ds by dt, which just simply gives me v over r. So omega, the angular speed, is v over r. If we were to rearrange this equation for v, we're going to find that v is equal to omega times r, and this here is one of the cornerstones of circular motion. The connection between linear speed, which is, remember, tangential. So let's say that we have a particle here. Oh, that was a terrible tangent. Let me just draw that one more time. The tangential speed v and the angular velocity, how much of an angle does it actually cover? As you can imagine, it depends on the radius. So the bigger the radius, the faster it will have to go to cover that distance. distance. We can take this even a step further by saying that since omega is d theta by dt, we can take some larger quantities. We doesn't have to always be dealing with infinitesimal ones, and say that this is equal to delta theta divided by delta t. And if we take delta theta to be 1 full lap, which is going to be 2 pi radians, divide that by t, capital T now for time period. However, remember, 1 over the time period is just the frequency, and that leaves us with omega is equal to 2 pi f, which is another incredibly useful and important formula in circular motion. Something which we don't often cover in school but does come up quite a lot is the angular acceleration. So if the angular speed is not constant, the whatever is moving can potentially accelerate. Let me show you actually. I've got a little badge over here, and if I was to rotate this at a relatively constant velocity, I could even accelerate this and produce some angular acceleration. The formula for this is d omega by dt, which by definition makes this the second time derivative of the angular displacement. Something that I've seen come up a couple of times, particularly in regional Olympiads, is this graph of omega against t, and if it's constant, such as the case in uniform circular motion, then it will just be a straight line. Notice that the area in this case will just be delta theta. Why is that? Because, well, d theta is omega times dt, so if we integrate that, we'll get that area. The angle as well changes linearly from some initial position or from some initial angle plus omega multiplied by the time frame by which the rotation has actually happened. Let's illustrate this rotational physics with a problem from the International Physics Olympiad. Okay, so we have quite a lot of information, as we can see, which is very typical for a difficult Olympiad problem. We have a rigid cylindrical rod of radius r is held horizontal above the ground. So this whole setup is above the ground with a string of negligible mass and length L. Then this whole thing is attached at point A and it is released. Now the trickiest bit is to really understand what's going on. The idea is that when you release the mass, this whole rod is actually rotating. The attachment point itself is moving, let's say, from here down to the other side. Okay, so now that we have an idea of what's going on, we're given a coordinate system. If we have a coordinate system, we'll probably be thinking about relative velocities, but more on that later. When the particle is at point P, the string is tangential to the cylindrical surface at Q. Okay, that's fine. And we're defined quite a lot of directions. We're given the unit tangent vector is t hat and the radial one is going to be r hat. The angular displacement, theta of the radius, okay, that's given. Once again, absolutely loads of information. Part A, so the string is taut, and in terms of the quantities introduced, find the relationship between theta dot and s dot. As we have just learned, theta dot is essentially our angular velocity. Now let's look back at this diagram. The trick is to realize that the length L is actually going to be a constant. Now as this thing is actually moving, we can say that the distance PQ, which is given as S, plus how much this thing has moved has to add up to L. So because this distance is S, I'm going to call this one, but X is just the arc length. Well, then I'm going to say L will be equal to S plus the radius R, and then multiplied by theta. Oh, not theta dot, just theta.
So what then I can do is differentiate both sides, because what I'm looking for is the relationship between theta dot and s dot. So let me just write that fully actually. dl by dt is equal to d by dt of s plus r theta. The derivative of L is 0 because the length is just constant. I'm just going to switch notations here. I am going to say that the derivative of, with respect to time of S, is just going to be S dot plus the radius is a constant, R, and then theta dot. Theta dot will just be given by minus S dot divided by r. And this was only half a point in the International Physics Olympiad. So part B, the velocity vq of the moving point q relative to the origin. Okay, right, well, let's make my diagram a little bit clear. So if we're standing on this point here, we're going to see point q to be performing circular motion around it. So as it is performing circular motion, it's going to have some tangential velocity. I'm just going to solve part B over here on the side. I'm going to say that V will be given by r omega, and this will be tangential. So we're given some vectors here. So I'm going to say t hat. Okay, well, the radius r, that was just sort of capital radius r. Omega is d theta by dt, or theta dot, and that's into the t hat direction. Then I can say that theta dot is minus s dot divided by r. So this will just give me r, and then minus s dot divided by r, and then t hat, like that. This here will just give me minus s dot t hat.
Back to more theory. So in circular motion, we always are going to have some centripetal acceleration. In problems, you can also see that being called the normal, in other words, the perpendicular to the motion equation. You can also call it radial because it's acting towards the center of the circle, or simply the perpendicular component. In this case, I've just given it this perpendicular subscript. Its magnitude is just given by v squared divided by r. And here is a proof of the centripetal acceleration equation. I have a separate detailed video on this that I'm going to link in the description if you're interested. It's important to note that anytime you have motion along any curve, there needs to be a radial or a centripetal acceleration component. Think about it, everything wants to move in straight lines unless there is some sort of a force that acts on it. Often you will see cases of uniform motion, meaning constant velocity along a curve. So if the velocity is constant, during the time when it actually is curving, there's going to be a normal component of the acceleration that's going to be given by v squared over r, provided there's that no slip condition. Because the linear speed v is given by omega times r, which we've proved already, we can also express the centripetal acceleration as omega squared multiplied by r. Please note that the length of the entire curve that you've kind of like been going along here will just be given by L naught, which is your, let's say, original coordinate, or the original position where you're at, typically taken to be 0, plus v, which is the speed multiplied by the time. This here is just distance multiplied by time. In exactly the same way as constant acceleration linear motion, you can have constant acceleration circular motion. Remember, alpha is typically the symbol that denotes the angular acceleration. So alpha is defined as the time derivative of the angular speed, and let's say that in this case it's some constant, but it's not equal to 0. Well, then omega, the angular speed, will be given by omega naught plus alpha multiplied by the time component. Think about it, this is just your SUVAT equation in the circular world, v is equal to u plus at. The units also make perfect sense. We have radius per second, and then radians s to the power of minus 2, which is this guy here, multiplied by s gives me s to the power of minus 1. If we wanted to find the actual displacement, this will be given by the original displacement plus omega naught t plus a half alpha, and then t squared. This here is our s is equal to s naught plus ut plus a half at squared. Please note that in this case s is your angular displacement, so I should have been more clear by choosing the symbols here. We can also have non-uniform circular motion, which can have both of these components. The perpendicular component will be given by v squared divided by r, and the tangential component will be given by the derivative of the magnitude of the velocity vector with respect to time. Please note that there's a big difference between the magnitude of dv by dt and the derivative of the magnitude of v over t. I know they look really similar, but if we think about it, this here is really the derivative of the speed. So for uniform circular motion, the speed doesn't change, so this here will just be 0. However, also for uniform circular motion, dv by dt does change because the direction of the vector constantly changes. So if we were to take away those two vectors, let's say here and here, that there will be some magnitude of dv by dt. So that's a really tricky thing that we need to be aware of. Another thing that comes up quite often in kinematics, and this is where often a lot of the harder problems are, is relative velocities. Now these can be a little bit confusing, I think mainly because of diagrams, but the main thing is to take it just one step at a time. First of all, let's define what a frame of reference is. It's just a whole bunch of coordinates and time, x, y, z, and t. That's it. In the very simple case of a one-dimensional coordinate system, let's imagine that we have this person over here that's just chilling by the road, and let's say we have somebody else who's driving in a car, and let's say that we take a distance to the end of the car, and I've called that distance x prime. So those two people, or shall we call it A and B, will measure different distances. Well, we can also define as the absolute distance or the absolute coordinate system as the vector sum of the above coordinates. In 1D, this is really simple because we either add them or take them away. If we were to differentiate as well, dx by dt was equal to dx naught by dt, there should be a naught here, plus dx prime by dt. And this gives me that the absolute speed will be given by v naught, which is the speed of this frame of reference, the speed of this guy, plus the speed of the car. Now notice that this person here doesn't necessarily need to be at rest. They could be jogging, for instance, in which case they're going to they're going to record a different distance and a different relative velocity. In the real world as well, though, we're not dealing in one dimensions.
Real shock, the world is not one-dimensional.
So for problems in flatland, 2D or 3D, we need to use position vectors. So we do exactly the same thing as before. R is going to equal to R naught plus R prime, where R prime is yet another coordinate system. I kind of like to imagine those two coordinate systems. I don't know, let's say X, Y, and Z. Let's say this one here is at rest, whereas this one here, this coordinate system, Z prime, X prime, and then Y prime is moving at some velocity, V prime along this direction. Well, the absolute speed v will be given by v naught plus v prime, and this is known as the Galilean velocity transformation. We can apply all of the standard laws that we know for adding or subtracting vectors in 3D space, and this is often where we might find little mathsy tricks to deal with. Classic example, if we have a person on a plane, imagine that this here is the inside of the plane. Take a moment to appreciate my work of art here. The plane is going, let's say, into the board at 50 meters per second. The person is walking at 1 meter per second. Well, if this thing is moving at 50 meters per second and the person is walking perpendicular to it, then the absolute speed will just be the vector sum of the above. The magnitude of this will be 50 squared plus 1 squared. Then we can work out the direction if we wanted to. Now, this gets quite a bit trickier when we're dealing with rotations. I have a problem here from the International Physics Olympiad on just that.
Okay, part C, the particle's velocity relative to the moving point Q when it's at P. Okay. So the best thing to do in those situations is to consider what happens a tiny amount of time afterwards. So if that's the case, first of all, this tangent point Q is moving, so it's going to move a little bit further down, and what we're going to get is that the particle is going to move a little bit to the right, and this is what makes this problem so tricky to actually visualize. So let's draw some triangles. I'm going to draw a little line here, and then we can hopefully visualize what's going on. So we have this new line. It differs on the radial coordinate. And how would it differ? Well, first of all, it's gone into the opposite direction. So for part C, the speed of the particle will have two components. One of them is going to be radial and the other one is going to be tangential. In the radial component, well, in a short amount of time, this thing will cover essentially a little arc length, which is going to be given by the radius. Our radius is just going to be S, and our angle is d theta. And in the limit in which this angle d theta becomes really, really small, this distance will essentially just be S d theta. So in that radial direction, but in the opposite one, because now we're going kind of to this way, kind of to the right, but r hat is pointing to the left, our vector will be minus not just s d theta, because that's the displacement, but the time derivative of this, which is going to be s d theta by dt. So we'll just write this as s theta dot. Okay, now our length s has changed a tiny bit. By how much? We're going to call this sort of like ds, and this will be our relative velocity in the tangential direction. The time derivative of this, which is going to be ds by dt, which is going to be s dot in the tangential direction. And this is really, really tricky to visualize. In a way, think about it, this vector is kind of pointing this way, this point is getting closer towards P, but r hat is pointing the other way. That gives us the minus sign here. The velocity is increasing relative to P in the tangential direction. Okay. Now, for part D, what we need to figure out is the particle's relative velocity to O when it's at P. So for part C, we calculated the velocity relative to the moving point Q, and for part B, we calculated the velocity of the moving point Q relative to O. So to figure out the particle's velocity relative to O when it's at p, this will just be the sum of the previous two velocities. So this calls it sort of v again, but relative to o. Okay, well, if we were to sum them up in the radial direction, the first component didn't have a radial the first velocity didn't have a radial component, so this here will just be minus s theta dot, and in the tangential direction, negative s dot and plus s dot will just cancel out, so there's not going to be any tangential component, so the answer should just be minus s theta dot.
Time to talk about something that appears all the time in physics Olympiads, and that is rolling without slipping. The condition for rolling without slipping is that the arc length covered by an angle delta theta is actually equal to the horizontal distance traveled. This can be a little bit tricky to visualize, so here is my bicycle wheel. Now, the basic idea is that if I was to turn this by one complete revolution, then in one revolution, if it was in contact with the ground, if it's rolling without slipping, it will move forward by exactly the distance given by the circumference of this, which is 2 pi r, or pi times the diameter. For one full revolution, the arc length is just going to be 2 pi r, so delta x will be 2 pi r. In general, though, we can say that delta x is equal to r times delta theta, where delta theta is in radians. Really important. Okay, so the linear speed is given by v. I've given a little subscript because that's the linear speed at which the center of mass of this wheel is kind of like moving this way. And if we were to bring the delta t onto the other side, we get that the center of mass velocity is equal to r delta theta divided by delta t. But hang on a minute, this is simply our omega, the angular velocity. So we get this really interesting result in which the tangential speed due to rotation is actually equal to the linear speed of the center of mass in the direction of travel. This means something remarkable. Imagine that this wheel is rolling without slipping. Consider the point of contact P. And now we're in the frame of reference of a stationary observer on the ground. So in the ground frame of reference, this whole wheel is moving this way. Basically, there's two types of motions. Let's see if I can sort of demonstrate that. It's like this, and then it's also moving like that. Now, if we focus on the contact point P, this will be moving due to the rotation with some linear speed, which is going to be equal to r omega, but also the center of mass will be moving this point this way. So this means that in the frame of reference to the ground, those two tangential velocities and center of mass velocities will be equal and opposite. And in our reference frame of us just looking at this from the ground stationary, this point here will be momentarily at rest. Notice that in the center of mass frame, so let's say that if we were here, the velocity of this will be the tangential r omega velocity at any point. Second condition, and that is slipping. And everyone who's seen a car kind of struggling to get going on ice or snow, for instance, or mud might have seen this. If that's the case, the arc length is a lot greater than delta x. If the car is just slipping in one place, then actually you can demonstrate that with my bicycle tire over here. So if I'm to hang on, let's try this again. If I'm to stay more or less still, this wheel is spinning over an angle, but it's not translating forwards or backwards. And this here is an example of the wheel slipping without actually moving backwards or forward. The condition for slipping is that the arc length is greater than delta x, where delta x is the horizontal distance traveled by the center of mass. Because of that, we can also say that r delta theta has to be greater than the center of mass velocity. In other words, you can also think about it as the spin tangential velocity is greater than the translational velocity. Questions in Olympiads tend to ask us about conditions for this to happen. Of course, we can also have skidding. I think that's what we call it, but essentially typically happens if you were to slam on the brakes, you don't have ABS in a car or something like that, and the wheel locks. And if the wheel locks, or it starts to skid, the arc length is less than the horizontal distance traveled delta x. If the wheel was to fully lock, then we can have even the arc length is 0, and this whole thing is just skidding and wearing out the tires. The condition for skidding to begin is that r delta theta has to be smaller than the center of mass translational velocity as viewed from the ground. Now, we've not talked about forces yet, but it might be a good way of introducing them. Tires don't tend to wear very quickly, and that is because rolling without slipping is actually an excellent approximation. At the contact point P, the frictional force F will act opposite to the direction of motion, and that is at 90 degrees to the direction of travel, meaning that no mechanical work is being done by the frictional force, and therefore we don't have to change our tires very often because that contact patch right over here, the frictional force, does no mechanical work. Back to rolling without slipping. This point here is instantaneously at 0 velocity because this velocity is going this way, this velocity is going this way, they're equal and opposite. I don't see so much people talk about all the other points, which I find really interesting. Now at point Q, on the other hand, well, Q is spinning this way, so the kind of like the spin velocity is going this way, but also the center of mass is also going this way, so both Vt and V sort of Cm, I can sort of draw it here, are in the same direction, so this will have a speed of 2 VCM, 2 R omega. We can even sort of like write that down if you wanted to. And that's the maximum velocity that a point will have during the rotation as viewed from the ground. And here is a little problem that I've just kind of made up for fun. We have a wheel of radius r is rolling without slipping with an angular speed omega. Find the magnitude of the velocity of a point horizontally to the center as shown in the reference frame of the ground. Okay, so let's start and think about this. Due to the rotation, this point P will be going down with some tangential velocity. Well, that velocity is just going to be given by r omega. Now, we're also going to be prepared because this thing is in contact with the ground, it's going to be moving this way, and if it's moving this way, it will also have the center of mass, and all the points are going to be translatingly, is that a word? Let me know in the comments. It will be moving this way as well. So we can say that VCM will also be given by r omega. Okay, well, the overall magnitude of the velocity is just going to be the vector sum of those two. So let's just put them tip to tail. Although we're just looking for the magnitude, always kind of like good practice to see what's going on. So the overall velocity will be pointing this way. And if this here is r omega, this here is r omega, I could then simply use Pythagoras. So I can say that V total, V, will be given by the square root of r omega squared plus r omega squared, which is going to give me 2r omega squared square rooted, which is just root 2 r omega. And you can play around by adding the vectors at any point onto the wheel to work out the direction of the overall velocity and its magnitude. Once again, the maximum one will be here. This one here will be root 2 r omega, and the contact patch will have an instantaneous velocity of 0. Now let's have a look at a pretty difficult problem connected with this from the Asian Physics Olympiad.
Look at this amazing problem. We have a cylinder within a cylinder. The bigger cylinder is called capital M, the lower cylinder is called lowercase m, and as the bigger one is rotating, the inner cylinder is also rotating without slipping. Okay, so the rotation of M is to be started from rest at instant t is equal to 0 when M is resting at its lowest point. So initially the low cylinder would have been somewhere here. At a later time t, the angular position of the center of mass of M is theta, and then M has turned through an angle of phi radians. How many radians would have mass M turned about its central axis relative to a fixed line? Okay, so this here will probably be a little trick, so I'm going to underline this. As with always with Olympiad problems, it's best to really understand the dynamics, the physics of what's actually going on. So if this here was a fixed point but not a rotating cylinder, so let's say if this here was a point P, well, this point would have gone somewhere just further afterwards after the rotation, and this would have traveled an angle which is given to be phi radians. So this means that the angle from here to there is just lowercase phi. Okay, well, the cylinder doesn't quite reach there because it's also spinning internally about its own axis and it's rolling without slipping. The amount that it has rolled, and we can call this its radius. We have its radius, don't we? Presume we have its radius. Yeah, we have its radius r. So the amount that it has spun would have been its angular displacement, which is given to be capital phi multiplied by the radius r, will be the difference between the two arc lengths. Phi multiplied by capital R, this is just this arc length here, and then take away the other one, which is going to be theta multiplied by r. So this means that the angular displacement will just be phi r minus theta r divided by r. There is a catch though, and the catch is that this is only true in the center of mass reference of this cylinder. In other words, if we were inside the cylinder kind of spinning with it, this is the angular displacement. Relative to the fixed line that I've specified, essentially OP, we're going to have exactly the same, but we're going to need to add another factor of theta. The cylinder doesn't just spin around its own axis, but it's also spinning by an angle of theta relative to this line here. We could simplify this a little bit further. I'm not sure if you get any extra marks for this, but you get the idea.
Well done for finishing the kinematics chapter. This next video will really help you prepare even better, so click over here.